In the previous class, we learned about the timing features of sequential logic. So especially, we covered the timing characteristics of E flip-flop. So it is because so you need to remember that this model. So this design model. So actually, okay. Now going slowly, going smoothly. So actually, this is typical is the system model that as I explained. So you need to remember this model. Okay. So between the two flip flops, there is a combination of logic. So and then the delay of this pass to this path. So which means that the output of this first flip flop and then until the input of this flip flop. So delay, it means the propagation delay determines the clock frequency. So it is, and then when we consider delay of this system, then we need to consider timing characteristics of the flip-flop, right? So you need to remember the definition of both setup time and hold time, right? So and then please remember this figure. So around the clock edge, we already know that the input of this flip-flop is sampled at the rising edge of the clock, but around the clock, so we there is some blind spot or some unstable timing. So it means that it is called the aperture time. But this is this cell time. This is the input signal needs to be stabilized before the cell time before the rising edge of the clock. Also, so this input signal needs to be maintained or kept after the hold time. Hold time after this rising edge of the clock. So you need to remember this definition of setup time and hold time. So it is because so also we need to consider propagation and contamination delay of output port of this deep class, right? So and then so I said that this is very critical for the performance of this system, right? So actually you will I believe so as a computer engineering student, you need to learn, you need to take the computer architecture course, right? And then, so in the computer architecture course, we will learn about the actually pipelining. So if we just apply the pipelining, we can reduce the clock period. So actually, so as I mentioned before, the clock frequency, so it is also the clock frequency is determined by clock period because frequency is the inverse of period, right? So clock frequency is very, very critical for the performance of a processor, the performance of a computer system. Okay, so and then everyone wants a fast computer system, which means that we usually need to increase the clock frequency. So which means that if the delay of this path determines the clock frequency, then we need to develop some ideas that can reduce the delay of this system, right? So that's why this timing characteristics of this sequential logic is critical for the computer system hardware. Okay, so we learned about the setup time constraint and hold time constraint. So actually, when we calculate the clock period, so allowable clock period, so it means that so in this system, the input of this building block needs to be stabilized. So which means that the output signal, the output value of this combinational logic needs to be determined, okay, finally finalized, right? So we can calculate the allowable minimum clock period of this equation, and then also we need to we need to meet the hold time constraint, and then this hold time constraint is related to the minimum delay of this circuit, right? So which means that this input of this flip-flop is to be unchanged, so it can stabilize the during the is hold time. So this is the equation for hold time constraint, right? So you need to also remember the this hold time constraint equation. So this is the example. So I showed the example here in the previous lecture. And then also I mentioned that we need to also consider the clock skew. So because every deeply block in chip receive the clock signal. Okay, so that means that as I mentioned, the clock is delivered via a metal line at a wire, and then so because this length is different, we can observe different delay for this clock signal, right? And then these different delays generate the clock skew. Okay, so when we consider the setup time constraint and then hold time constraint, then I also mentioned that we need to consider the clock skew. But just to remember that we need to consider worst case, right? So when we design a system, then we need to consider worst case, right? Why? So if we can avoid the worst case, then we can build stable system. So sometimes, so you may think that we can just consider some average situation or some normal cases, but it's not true. So the average means that in the probability theory, the average is just here, okay, right? So, but we need to avoid these some severe cases or worst cases for our real world scenario. So it's also same to this clock period. When we consider the clock period, then we need to also consider the clock skew, but the worst case scenario. So which means that, so actually, you just remember that if we just consider clock skew, then we can just consider the worst case. So which means that what is the worst case? What is the worst case for clock period? The clock period is increased, right? Because it's not good for the performance. So which means if we actually this is the equation of the setup time constraint, but when we consider skew, then the clock skew is to be included in this setup time constraint equation. Hold time is the same, so we need to consider the worst case, right? So this means that the hold time. So when we consider the hold time constraint, then the clock skew is added to the hold time. Okay. So those are what we learned in the previous lecture. Actually, when we build the system, then this timing is very critical because these constraints are violated. The timing constraints are violated and system becomes unstable. Okay, we need to avoid this situation. Okay, so now, I will cover the another issue of the unstable sequential logic. So case, so it's synchronization. But so I believe you don't need to really understand the mechanism of this synchronization, but you need to know how to avoid. Actually, you cannot avoid the this actually this case is called the metastability. That means the unstable scenario or unstable situation. We cannot avoid this situation perfectly, but we can reduce the probability for this situation. So we will cover this another issue, that is the synchronization. Okay, let's think about this system. So what can you see? You can see this is the button that you are switch, and then the output of this button is connected to the input of the flip-flop. So actually, this is the outer interface. So you mean so things like this, you can just push the usually. So recently we use the touch screen, but actually the previous generation of the smartphone, so this phone has a button, right? So it's like this. So we can just push button, and then actually if we push our buttons, then this system or button system generates some electric signals, right? So and then so our system is the system. So which means that when we push the button, then we can think that the output of this system will generate only two values, right? Because we are learning about the digital system, right? The 1 or 0. But so actually we learned about the digital display, and then we also learned about some signal characteristics of this digital system. But we can say that the output of this button will generate 1 or 0. But this is the this is the D flip-flop. So which means that we need to also consider timing. Timing of this input signal. The output of this button system is the input of this D flip-flop. Then what's the problem? So this is the case 1. So and then D is the output of this button. So and then this is the clock signal. If this D signal is determined before the setup time, right? So this is the case 1. So D is stabilized. So D becomes the 1 before the setup time of the D flip-flop, right? Then it will work properly. It will work correctly because this case does not violate the setup time constraint, right? So it's okay. This is okay. How about this situation, case 2? It's also okay, right? Because the D is changed after the hold time of this clock, right? This D flip-flop. So this is okay. So we can observe the proper output at Q output of this D flip-flop, right? But how about this situation? So so this signal D changes during the aperture time. So there is the setup time or hold time. So actually it violates the setup time or hold time constraints of this D flip-flop. Then what will happen? We don't know. So I said that if the input of this D flip-flop violates the setup time or hold time constraint, then we don't know the exact value of Q. So this is the case 3 is this situation. This case 3 violates the setup time or hold time constraint. But so if is inside of the system, like the input of this combination logic is the output of the flip-flop, and then the output of this combination logic is connected to the input of this flip-flop. So inside of this is the system. We don't need to consider this case 3, right? So actually we need to beat this setup time constraint or hold time constraint when we use the system. But this is the important situation. Why? The bottom is the outer interface, so which means that we cannot control the timing of this button. So this timing of a button is actually determined by users. Okay. So the problem is that we can encounter this situation case 3 for this outer interface or outer user interface. So what's the problem? So actually, so when a user pushes the button, then this user will generate the input signal to this flip-flop, and then the output of the flip-flop can be unstable, right? Then how can you avoid this situation? And then what will happen if the input signal changes during approach time? So this situation is called metastability. Actually, this case is called metastability. So metastability means that the states of this system or flip-flop or sequential logic is in the unstable state. That is called the metastability. Then what is the unstable state? So in the digital system, if the signal value has 0 or 1, then we can say that, oh, this system is stable. But if a signal value, we cannot decide the signal value. For example, if the signal value is around the half of VDD, then we cannot decide the exact value of this signal, this electric signal. Okay. And then sometimes because of the unstable time issue, like the case 3, so if our input signal violates the setup time or hold time constraint, then we can observe this metastable state. Okay, so which means that we don't know which value will be the output of this flip-flop. Also, we cannot avoid this situation, right? Because we cannot arrange the input timing of this flip-flop, because the timing of this system, the timing of this input of this flip-flop is determined by user. We cannot expect the timing of this input. And sometimes if this is the timing is random, so we can just calculate the probability of this case 3, but you cannot avoid this situation. But problem is that if this is the interface from user, but this interface generates the unstable signal. then this unstable signal can be propagated to the inside of the system. Then what's the problem? Then our system can be also unstable. So that's the problem. So we need to avoid this situation. Then how can we avoid this situation? So actually our system our smartphone or computer system interact with the user interface, right? So we can just push the keyboard, we can just move the mouse, or we can just touch the touch screen. That is we cannot control this timing of the user interface, right? Then how can you avoid this metastable states? So actually, firstly we can okay. So I will briefly explain some property or characteristics of metastability. So actually you don't need to understand the exact mechanism of this metastability. So this is the really complex. Actually this is rather the analog circuit issue, not the digital circuit issue. So actually we can just define the probability of metastability like this. Okay. So this probability function represents that this is the probability that output Q is metastable vector. Okay. So that is a probability. So it's just a probability. It's a probability function. So we can just define the probability of metastable like this. Okay. So as you can see, this is the inverse of exponential function, right? So this is the kind of constant value, and then this is also some coefficient of this function, and then this is the t. Then this probability is determined by t. So what does that mean? Actually, the probability of metastability is higher. Okay, it's high if the t is small, right? Just this t is small, but this probability is reduced exponentially. Okay, if the t is higher, okay, t value is larger. Okay. Then, so this is the probability function of the metastability. So actually T1 is the time to resolve to 1 or 0, and then T0 or tau is the properties of this circuit like flip-flop. So we can understand so I mentioned that this function is generated from some analog features of this flip-flop. So I will. So it's not easy to understand this function, the analog circuit, but we can intuitively understand the meaning of these vectors. Okay. So actually in this equation, TC is the clock period. Okay. And then so TC is the clock period, and then T0 is divided by clock period. So we can say that this is the probability. So input, the users can push the button, but the users can push the buttons randomly, so at random timing. So which means that actually if we can avoid this case 3, which means that if the user push the button outside of the zero time or hold time period, then it's okay. The system will work properly. But if the user push the button during the approach time, like stage 3, then the system will well, not real. This system can work incorrectly, It's because this is the function of probability, right? So we can understand that is T0 divided by TC is the probability. It's probability that user can push button during the aperture time. So this long time clock period, the users can violate the hold time constraint or setup time constraint. If users can push button during this hold time or setup time, then we can. So that view, so we may observe the metastable state. So we can understand that T0 by Tc is the ratio of aperture time over the clock period. Okay? Then how is the time, the required time that can be required, how is the time that can be required for escaping from metastability? Okay, that is the property of circuit. Okay, so but if we see that this function, if we see this probability function, then we can understand that if we wait a certain long time, if we wait long time, then the probability will reduced. Okay, that's what we can know from this probability function of metastability. Okay, then how can you avoid the metastability? So actually, we can avoid the not avoid. So we cannot avoid the metastability entirely, because if you see that this function, then you can say that the probability cannot be zero, right? It's because this is the inverse of exponential function, right? So the probability does not go to zero, even though the t is very long, right? T is very high. Then how can we cannot avoid the metastability entirely, but we can reduce the probability of metastability, probability of failure very low. So fortunately, its function is the inverse of the exponential function. So which means that if the t is large, then we can extremely reduce the probability of metastability, right? So using a synchronizer, we can reduce the probability of metastability significantly. Okay, that is the goal of synchronizer. And what is the synchronizer? Actually, it's simple. Synchronizer looks like this. It's a series of multiple flip-flops. It's very simple, right? But for the outer interface, if our digital system receives a certain signal from the outer world, then we need to design synchronizer for this outer signal, because we don't know the exact timing of this outer signal. So synchronizer looks like this. This is the series of multiple flip-flops. Then how can we reduce the probability of the metastability? So this is the outer signal. E is the outer signal, and then this flip-flop F1 is connected to the outer port D. And then let us assume, so we don't know the exact timing of this D. So let us assume that the metastability is observed at this F1, flip-flop F1. But after some time, so this is the failure of metastability. The probability function looks like the E minus T divided by tau. So it means that after some time, then this signal can be moved out from the metastable states. Okay, so after some time, then the signals can be 1 or 0. But with the high, it's also the probability function. With the higher probability, if a user push the button during the aperture time, then we may observe metastability at this flip-flop F1. But after some time, the signals can go to 1 or 0. But we don't know the exact value of the signal, this output of this effort during this time. Okay? But so after some time, the signals can be 1 or 0. Then this F2 can receive clean signal. Okay, so it's a stabilized signal. So that is the actually that is the mechanism of a synchronizer. But this is very simple, right? So by using the back-to-back flip-flops, like the series of multiple flip-flops, then we can reduce the probability of metastability very low. Okay? But you need to remember that if a certain signal is connected to the outer world, okay, we don't know. If we cannot expect the exact timing of the input of the flip-flop, then we need to add the synchronized circuit like this. So sometimes also inside of a chip, the clock space can be different. Like this flip-flop is connected to the clock. Clock 1, or this flip-flop is connected to the clock 2. And then in the system, that this flip-flop can receive the output signal from this clock space. It's called the clock domain. If a certain system works with the same clock signal, then it is called the clock domain. But sometimes inside of the same chip, we can use the different clock signals. So in this case, and then but a different domain can receive the output signals from a different domain, right? So this domain can receive the output signals from this clock domain. So in this case, we can also, we don't know the exact timing of this clock domain compared to the pure clock signal of this domain. So in this case, also we need to use the synchronizer. Okay. So just remember that if we don't know the exact timing behavior of input signal of the system, then we need to add the synchronizer, not reduce the probability of metastability. Okay. This is synchronizer. Oh, it's very simple, right? So we can just remember the synchronize why we use synchronizer for the different domains, different clock domains or interfaces to the outer world. Okay, so this is the failure function of the synchronizer, and then actually this is this is the important metric for the reliability of the system. So reliability of the system represents the stability stability of the system, but I will not cover this slide, but because this is also not. So actually, if you learn about some advanced topics in computer architecture, and we can also learn about them. Is mean time between failure and TDF. This is related to the reliability of a computer system. But this is the advanced topic, so I will not cover this TDF in this course. But just remember that so reliability of a computer system is also an important issues in the computer system. So think about this: the many big companies like Google or Microsoft, whatever, Kakao, they run very large data center, right? And then these data centers can do the public data. That means that the data from many users, the large number of users. Then in this system, the reliability is very critical, right? If the user data is corrupted in the data center, then we cannot use this data center. So, for example, we can just store our data in the Google data center, Google Cloud, but if our data is removed sometimes, or our data is corrupted, then we cannot use this data center, right? And then we will also need to that our money, well, they need to actually pay the large amount of money to the customers. So that's why the reliability is critical, but actually the synchronizer, the meta stability is also the kind of it's a relative the kind of reliability issue. But just remember that using a synchronizer like this, so just remember that the meta stability can be can occur because of unexpected timing to the input of it will not or sequential logic, and then we can avoid meta stability using synchronizer. Okay. So actually, so we can explain this reliability where it's actually reliability. The reliability of system using the probability function. So that's why the probability is also an important topic in computer engineering. Okay, so this is the end of the chapter 3, and please read the chapter 3.5 for these timing issues of sequential logic. Okay, so let's move on to other topic. So this is chapter 5. Okay. So now, I will cover some different topics in this logic system. So this is the arithmetic units. So okay, so actually we learned about the combinational building block, like the multiplexer or decoder, right? Then what is this building block? So what is digital building blocks? So these are the very basic modules that can be used for the more complex system. So we learned about the gates. So these gates also that is the basic gates are basic components that can be used for building these modules. Also, we learned about the multiplexer. Multiplexers are also frequently used. The decoders, the registers. Registers are group of different blocks. And then we also use these blocks very frequently. So like the arithmetic circuit, and then counters like 1, 2, 3, 4, 5, there's a counters, and memory, and then logic arrays. So we frequently use these blocks in the complex system system. Because using these basic building blocks, we can build a more complex system hierarchically. And then we can use the module of basic building blocks to build the more complex system. Okay? So that's why we need to learn about the basic module of this building block. Okay. And then in this time, so we will learn about the arithmetic units. So what are arithmetic units? So what are arithmetic operations? So those are adders, subtractors, multipliers, or dividers. So that means that actually, so our computer system, our computer processor handle number data, right? So actually, so all data is numbers. So all data are numbers, right? And then in order to handle this data, then we need to process numbers using operators. So actually, when we write software code, we frequently use the add, minus, multiply, and divide operators, right? Because in the real world, we frequently use these operators, right? That means in order to support the required functions for these operations, then we need to build the arithmetic units that can support these operations, like adding, subtracting, multiplying, or dividing. Okay, so these are basic arithmetic operations: addition, subtraction, multiplication, and division. And sometimes we may require special functions like the square root or sine or cosine functions or something like that. And then in order to support these functions, then we need to build the distant circuit or distant module. Distant module for this function, right? So in this chapter, actually in chapter 5 of the textbook, so we will learn how to build the basic arithmetic units first. Okay. So firstly, so we will learn about the basic arithmetic units, and we will learn about the basic modules that can be built with the flip flops. Okay. So those are frequently used components in the computer system, like ALU, like the arithmetic logic units. Okay. In the processor, we use the ALUs for executing arithmetic instructions or arithmetic or logical instructions. Also, in order to handle floating point numbers, okay, so actually in this course, we just learned about the integer numbers, but in the computer architecture course, also we will learn about the floating point number systems. And then in order to handle the arithmetic operations for floating point numbers, then we need to also build the floating point units. So actually in the machine learning or AI applications, those applications handle floating point numbers, right? The deep neural networks or some the neural network application really have the floating point units. Also, by using these arithmetic units, then we can also build the custom processing engines. Okay. Okay, so let's start with the addition. Okay, we will learn about the half adder and full adder. So let's review the add operations using add operation for integer numbers. Okay, so for add operation, then we can just perform the add operation for each digit, right? So actually, so these data, these numbers, for actually, we just focus on the each digit of this add operation. Then for each digit, we require two input values, or if we just perform the add operation for this digit or column, then actually we require three inputs, right? And then which outputs are generated for this operation? So for this operation, like so here for this digit, okay, for this digit, the logic gate receives the two input, and then sum this value is generated, and carry is generated, right? So actually, if we just focus on this digit operation, then this operation requires the two inputs, and then it generates the two outputs. Okay, but also, and then if we just see this digit operation, then this digit requires the three inputs, and then generate the two outputs, like this sum and then carry. So actually for this add operation, the we need to build the digital circuit that performs that supports this operation, right? And then these are called adders. Adders are used for performing add operation. And then based on the number of inputs, then we can distinguish the adders like the half adder and full adder. Okay, so let's see the half adder. So I mentioned that so sometimes for certain digit can we require two inputs, right? Like this. So this digit requires the two inputs. So actually we can design the half adder that supports the two inputs. Okay. So you can generate and then this adder will generate the output, two outputs like sum and carry. And then this carry is called carry out. This is the carry out. Okay, and then this carry, because this carry will be delivered to the next digit, right? So it's like this A plus B, and then the sum is generated, and then carry out is generated. Okay, then we can easily fill the truth table for half adder, right? What is this C? What is S? So let's think about S first. So 0 plus 0 equal, it's 0. How about the 0 plus 1? It's 1. How about the 1 plus 0? It's 1. How about the 1 plus 1? What is this S value? It's 0. Why? Because the carry is generated, but S will be 0, right? How about the C out, carry out? So you know the 0, 0, no carry out, no carry out, no carry out, carry will be generated if the 1 plus 1. And then if we see the truth table, then we can easily generate the Boolean equation, right? So S is the A exclusive or B, right? So 0, 1, 1, 0. So if the A and B is different, then this is 1. That means the exclusive OR. And how about the C out? C out is the A and B, right? The AB. This is the AND, right? So half adder, so we can easily generate the Boolean equation for S in the sum output and then carry out output. But usually for this digit, we require 3 inputs. So 1 input from two inputs from A and B, and then another input from generate from previous digit, right? So actually, this is the general adder, because if we see that adder operation, only this digit requires two inputs, but other digits require three inputs, right? The carry from previous digit. So actually, we use the full adder. So full adder has the, as I mentioned, the full adder has the two inputs A and B, and carry in. This is the carry generated from previous digit. And then also the full adder generates the sum and C out. So it looks like this. This is the A, this is E, and then C in is a carry, and then plus, and then this adder will generate the S, and then C out. Right. Then we can easily, if we just understand the operation of full adder, then we can easily generate the truth table for this full adder. Right? Let's start from the S. 0, 0, 0, so obviously 0, 0, 0, 1. It's 1, so 0 plus, is a 0 plus 0 plus 1, right? So 0 plus 1 plus this is also 1. How about this one? It's 0, right? It will be 0, 1. So same 1, 0, 0, 1, right? This is 1, and then this is will be 1, 1, and then 1, 0, 1, 0. Right? How about the C out? C out will be 0, 0, 0, 1, 0, 1, 1, 1, right? So, and then based on this truth table, and then using the column, and you can generate the optimized Boolean equation for full adder, right? So actually the S is the A exclusive over, B exclusive over, C in, right? And then C out. C out is the A B, B C in, and then AC in. So this is the Boolean equation of S and C out of this. Okay. So actually this is answers for the previous slide. So we can build the full adder and half adder, and then if we see the half adder, so this is the truth table, and this is the Boolean equation, and we can build the half adder like this, half adder circuit like this, and then so you need to understand that the half adder has only two inputs, A and B, and you can just build the C out, carry out, and sum. Okay, so you can the circuit can be built like this. Okay, and then full adder, as I mentioned, the full adder has three inputs, A, B, and C in. Okay, and then you can build the Boolean equation like this. And then full adder looks like this. So this is A and B, and then carry is delivered from the previous digit, and usually we locate the carry in the right side of the circuit. And then the carry out is generated, and then this carry out will be delivered to the next digit, and then the S will be generated. Okay, this is the circuit for addition for each digit. Okay, this is the basic element for performing adder operation for each digit. That is the full adder. Then how can we build the adder for larger number? Okay, this is just the basic element for bit-based adder operation. But then by combining these full adder then we can build the adder unit for larger number. Okay, so for the multiple bits. It is that actually so. So let's think about the multi-bit adder. But if we just know how to perform the binary addition, then we can build the multi-bit adder easily, right? Because we learned that the firstly for addition we can start from the LSB, right? LSB operation, and then carry is generated, and then with the generated carry, then we can perform the next digit operation, and then carry when will be generated, and we can just perform the add operation for next digit, next digit. So how can we connect these two adder for multiple bits? So actually, if we understand how to perform add operation, then we can know that actually the C in is the carry in, the C in is generated from the carry out of the previous adder, and then also this carry out is becomes the C in of the next adder, like this. So actually the carries are connected each other, and then ABs are given from the input in parallel. Okay, that is the multi-bit adder. So you need to understand that carries are, when we compose multi-bit adders, then the carries are propagated from LSB to MSB, right? So carries are propagated. That's actually very important because this carry propagation determines actually the carry propagation is the critical path. That is the longest delay path in adders. Right. As I explained, actually the AB, these inputs are given from the out of adder, but in parallel. Okay, so if the input signals are given in parallel, then we can parallelly perform this add operation. But how about the carry? So when we perform the add operation, then we can observe that the carry is propagated from the previous digit. Okay, so actually the carries are propagated, and this carry propagation determines the longest delay of adder. So actually there are multiple types of carry propagation adder. So it's a ripple carry adder, carry propagation adder, and prefix adders. Why? Why do we need to learn about the multiple types of carry propagation adder? So it is because delay. So when you learned about the sequential logic timing, so this is the combinational logic. So actually the adder is the combinational logic, and then using this adder, then we can build the arithmetic unit. But this is the combinational logic. So combinational logic is located between two flip-flops. So what does that mean? The delay. So TC, clock period is the function, is the actually it's larger than the delay of this combination logic. The delay of this path, so it needs to be include the setup time or propagation time of the different clock, and then clock skew. But propagation delay of this combinational logic is also included, right? And then actually the delay of combination logic occupies the large portion of this delay. Usually the setup time or clock skew is small. then what propagation delay of this combination logic occupies the larger portion of this delay. Then in order to use the test clock, so which means in order to increase the performance of our system, then we need to use the test clock, which means if we can reduce the delay of this combination of it, for example, if we can reduce the delay of adders, multi-bit adder, then we can build the faster adder. That's what. So you also you can find that there are three types of adder here. The ripple carry adder, slow, carry adder, fast, prefix adder, faster. So in order to reduce the propagation delay of this carry, then researchers proposed the different types of adder. This is also very critical for the performance of NPU, the neural network, neural processing unit, like the Google TPU. Is because the adders are the main part of this processing engine. Okay. Then later on, so you need to, so actually in this course we will learn about these three types, actually 4 types of adder, but the purpose of the different types of adder is to reduce the carry propagation delay. Okay, let's think about the ripple carry adders. So ripple carry adder is a basic adder that can be built from 4 adders. So as I mentioned, we can build the multi-bit adder by combining 4 adders, right? Like this, actually. This is the circuit. This is the multi-bit adder logic that can be built from 4 adders. Right. So this is the LSB, and then A0 and B0, then we can generate S0. And then this adder can also receive the carry in from the default adder. And then from the LSB, the carry is generated C0. Okay? This is the C0. And then this carry is propagated to the next digit, is the 1st digit. And then using the A1, E1, and C0, the S0 is generated like S1 equal A1 exclusive over B1 exclusive over C0, right? So S0 generated also carry will be generated from this full adder, right? C1 equal A1 C0 B1 C0 plus A1 B1. So we can observe that in order to generate the S1 and C1, then we require C0, then C0, C0. Right. So the carry is generated propagated to the next digit. And what's the problem? How about the S31 and C out? So S31 requires the C30, and then we also know that C0 is requires the C29, and then blah blah blah. So in order to generate the MSB S31 or C out, then carry needs to be propagated from the C into C30. So it can mean this is the critical path. So that's the longest delay of the ripple carry adder. Okay, that means it can be very, very slow, right? The carry is generated from LSB to the MSB, all right? And then the carries are not to generate the carry, and we require 2 input AND gate, okay, 2 input OR gate, right? And then these gates are connect it again and again and again. Then the last carry, the MSB or carry over MSB is generated. So it's extremely slow. Okay, so when we calculate the delay of this ripple carrier, then we can understand the delay of the ripple carrier like this. So in this equation, the TFA is the critical delay. So that means the longest delay of the full adder. And then which means then for this NB ripple carrier, the longest delay can be the n times of longest delay of full adder. Why? Because the carry is just propagated via full adder again and again. Right. So this is very simple. Okay. But we can understand that if the bit width is very large, and if we just handle the 32-bit integer or 64-bit integer type, the 64-bit the long integer, then delay is extremely large. Then it means that our computer system can be very slow because of ripple carrier. Okay, it's extremely slow. So in order to avoid this disadvantage of the ripple carrier, researchers developed the carry required adder. Okay, just remember the definition of the required. What is the definition? To think about what will happen in the future and plan. So it's just definition of the required, but in the required adder, required means that the carry is generated faster. Okay, so that is the definition of the required. So think about what will happen. Think about the future quickly. That is the meaning of the required. So look in the required adder, then the researchers propose the carry generation. With carry generation function that can be computed and faster, more quickly compared to carry before adder. Okay. Okay, so I will stop here. Then thank you for your attention. Let's see you in the next class. 감사합니다.